Today we're going to go over light behavior. And let's make this bigger. So you should have let me kind of show you really quick. You should have a handout, okay? The handout, you're gonna be filling in the stuff that's missing, okay? So for example, here I have reflection of light. See, all this stuff is missing. Reflection occurs when a wave bounces back after striking a barrier, a reflection in a mirror. So all of this, you need to start typing in right here, okay? You need to start typing in right here. And you'll know when to stop typing because like here it says example of reflection in a mirror. So obviously you're not going to copy this part. So this is the part that you're going to start writing, okay? So one of the things that you can probably do is you can probably have the handout, where is it? You can probably have the handout kind of like this, and you can kind of maneuver it to where, maybe just maneuver it somehow to where you can kind of see the this part, and you can start typing in anything that's missing. Okay, so there's going to be a lot of stuff that's missing that you need to start typing in. Okay, so reflection occurs when a wave bounces back after striking a barrier. So here you have light and it's hitting a surface, right? And it's going to bounce back. So you have a mirror, for example. There are three things that affect how light is reflected: the surface, the color, and the shape of the object. So you might have a smooth surface or a rough surface, right? So water can be smooth or it can be rough. And depending on how smooth the surface is, the reflection will be almost identical, right? The color of the object can also depend on how the reflection is and the shape. So if you have a mirror that's a concave or convex mirror, okay, that could be an example of how light can be reflected off from those three different things. Okay, so the surface of the object, clear versus diffuse reflections. So smooth, shiny surfaces have a spectacular reflection. So if you have a smooth surface, the light that hits it, it's going to bounce off. And notice here the angles here are nice and neat and perfect, right? So that's going to give you a spectacular reflection. Okay? A rough or dull surface, like let's say this was water and it was windy and there's a lot of waves. Yes, you're going to get reflection from the water, but it's not going to be a nice reflection like if it's a very still water, right? And why is that? Well, as light is coming down, it's going to hit these little crags and crevices, and it's going to kind of deflect it at very odd angles. Okay, so rough dull surfaces have a diffuse reflection. Diffuse reflection is when light is scattered in different directions. Okay. So an example of this should be spectacular reflection and a diffuse reflection where the light is going to kind of go off in all those areas. So here is smooth water, right? Looks like a mirror. And you have wavy water. Doesn't look as nice. Okay, the color of the object. So if you've ever noticed that a driveway, an asphalt driveway, seems hotter on a summer day than a concrete sidewalk. So why is that? So I'm pretty sure when you see this part of the street, you're gonna see kind of the heat rising, right? And it's gonna kind of be wavy, right? As opposed to like concrete. So why does this happen? Well, this happens, why does the little wavy part happen? And you can see the heat from far away. Well, this occurs because light that is not reflected from the surface of an object may be absorbed by the object. And it's going to be converted into thermal energy. So you're going to see that in black surfaces. The darker the surface, the more it's going to absorb the heat, and it's going to convert it into thermal energy. Now, concrete, if you were to kind of zoom in on concrete, it has actually like these little tiny, very tiny holes that lets air in and out and so on. Depending on how the concrete was poured, what kind of sand they use, and stuff like that. Some concrete is going to be a lot tighter, and if you were to step on it with, like, let's say your bare feet on a hot summer day, then it would be a lot hotter than, let's say, concrete that if they used really bad sand or not a good type of concrete, or maybe they put more sand or more concrete, like, so it all depends, right? Okay. But here the asphalt is, since it's black, it's going to absorb that heat and it's going to convert it into thermal energy, and you see the little steam. It's almost like little steam rising up, right? It's not really steam because steam is with water, but you're going to see the heat rising up. So this is actually really important. I don't think it's on that handout, so I highly suggest that you copy this. So here you have the shape of the object, okay? You have a mirror. This is called the incident ray. So again, copy everything that's on here, okay? Somewhere on there, or actually on your notes somewhere. You're gonna need to copy this down, okay? So here you have the incident ray. The incident ray is where the light is coming from and it's hitting the mirror and it's reflecting off it, okay? This is called the angle of incidence, and this is called the angle of reflection. So like I said, this is very important. There's always at least one or two questions on a test that asks what is an angle of incidence or angle of reflection. If you have a mirror, the angle of incidence is going to be the same of the reflection. So if this was 30 degrees, this would be 30 degrees. If this was 50, this would be 50. Okay. Yeah, so that kind of explains that part here. The law of reflection. Angle of incidence equals the angle of reflection. The incidence equals the reflection. Okay, they are the same. So in other words, light gets reflected from the surface at the same angle it hits it. Okay. So here you have the angle of incidence, angle of reflection, right? Little picture there. So there are different types of mirrors: the flat, the concave, and convex. Okay. I think, no, this one's the concave and this one's the convex. So concave, you want to kind of picture it like a cave, right? Cave. Convex would be the opposite. So here you have a flat mirror, flat surface. The light is reflected straight back, resulting in an upright image that is the same size as the original object. Right? So you're standing there like the lady here, the light goes there, the light bounces back at that exact angle, which was, I mean, depending on where you're standing, right, it's going to give you an exact duplicate, right? Okay. So here you have your concave mirror. So the concave curves inward like this. uh, I mean, the way I like to picture it, it's like you're gonna go into a cave, right? So concave mirror. So curves inward like the inside of a bowl. If an object is very close to the mirror, light is reflected in a way that an enlarged upright image is produced. If the object is very far, the image is reduced in size and upside down. So depending on kind of where you're standing, if you're standing way back here, uh, or close up, the image is going to be either very large or it's going to flip the image upside down. I'm sure you guys have all been in those funhouse mirrors where you're standing at a certain angle and you're kind of like really big or really skinny, or your image is upside down. Okay, so if you're standing right here, I believe the image should well, I mean, depending on where you're standing, okay, that's what's going to happen. You're either going to be very large, or the image is going to be very well, it's going to be upside down. Okay, and the reason being is as the light comes in, it's going to kind of reflect it like this. Up is going to be down, and down is going to be up. So it's going to flip the image. For a real object between F and the mirror, a virtual image is formed behind the mirror. The image is upright and larger than the object. So, I mean, all you have to know is just, depending on where you're standing, it's going to kind of, the image is going to be either big or small. So we're not going to really go too deep into this part. Now let's go into convex mirrors. They curve outward. It results in an image your eyes detect as upright and reduced in size. So if you notice the mirrors that you have here on your car, they are actually convex mirrors. They're gonna make everything appear closer. The reason you want to do that in a car is you want an object to appear closer than it really is, so that you can judge like distance. You can have at least a split second to avoid that car that's going to crash into you or move out of the way. And those split seconds, especially if you're moving really fast, they do matter. Okay, a second, less than a second, they do matter. So the side mirrors on cars are convex mirrors. Objects in mirrors are closer than they appear. And they'll even have that little thing there on some cars. And this is, like I said, all depending on kind of where you're standing. So if you're standing here, the object, the light is going to kind of go this way, boom. And then this one is going to come this way, and it's going to reflect down here. And so it's going to make the object look larger, right? The light's going to reflect going this way up and going this way, thereby making the object larger. So if you've never done this with a spoon, you can try it out. Because the spoon, if it's a very, very shiny spoon, you can look at the inside of the spoon, which is convex, I'm sorry, concave, and the outside of the spoon, the bottom part of the spoon, and that one's convex, right? So here you have the outside of the spoon, and the image is going to appear maybe a little larger or closer. And the inside of the spoon, which is the concave, right? This is the concave, this is convex, it's going to appear upside down. What I suggest that you do on your notes is maybe do a quick little sketch of this. That way you can have the difference between convex and concave. Maybe just draw a spoon, and you can kind of draw a quick little sketch. Okay, refraction of light is the bending of a wave as it passes from one medium to another. So light is going to somewhat slow down as it passes from air to, let's say, water, okay, liquid. So that is called refraction. And the mediums are solid, liquid, or gas. Okay. So here, what causes the light to bend? Well, it's the density of the medium. Okay, so in air, you have these little molecules that are kind of spread out apart, right? And in water, they're a little bit closer together. So it's going to be a little harder for the light to kind of go through there. It's going to hit one of these little water molecules and it might just kind of slow it down. Okay. Here, the light can kind of, it's got all this empty space to pass through. Here, the light is going to have to kind of find its way to pass through it. So density is how much mass there is. If there's a whole bunch of them, the density is higher, right, than this one. So here's an example of refraction. This is when you have a pencil, a straw, and it looks like it's bent or cracked, right? So in this case, the light rays are slowed down by the water and are bent, causing the straw to look broken. The two mediums in this example are air and water. So here you have light, right? Light is going through, passing through air. But when it passes through, so here it's passing through air, but when it hits water, it's going to slow down and it's going to make the object appear like this. Okay. Let's move on. Another example is when you use a magnifying glass. The object appears larger because of refraction. So can light pass through, we saw it pass through a liquid, but can it pass through a solid? Yes. Glass is a solid, right? So here you have light, it's passing through. It's gonna kind of slow down a little bit and it's gonna pass through over here, okay? And here you see where it's gonna kind of bend the object, okay? The light waves traveling in the air change direction when they enter the glass of the lens and then again when they move from the glass back into the air again. Okay, we're going to move on. Okay, now we have convex lenses. They are thicker in the center than the edges, and the lens that converge brings together light rays. So here you have light coming in, and it's going to kind of bend it, right? It's going to bend it, okay? It's going to slow it down. This form real images and virtual images depending on position of the object. I suggest that you guys maybe copy this in your notes, do a quick little sketch of this. And here you have the object or the that you're trying to read. It's gonna kind of make it a little bit bigger for you to see. Okay, so the drawings are really important for you to draw those. We're not going to go over this equation. Concave lenses. These are lenses that are thicker at the edges and thinner in the center. They're going to make objects small. Okay. And I suggest that you maybe do a quick little sketch of this, showing kind of what's happening to the light as it's passing through there. through the little lens. I'm sure you guys have all seen at one point maybe held some binoculars, and if you see it in one direction, the object's going to appear larger or closer. And if you reverse it, if you use the opposite end, it's going to appear smaller, right? And that's because of the lens that you're looking at. You're kind of changing the lens. Okay, diffraction of light is the bending, spreading, and interference of waves when they go through a narrow opening. Okay, let's go to the next slide. Okay, so now we're going to go into diffraction patterns. And diffraction patterns, this is how light and even sound can kind of travel, okay? So here, you're going to have to copy this part in your notes as well, okay? Because I don't think it's there in that handout, so you're going to have to copy this part here. But this explains how light and even sound, how it travels around objects. So here you have radio waves. They can diffract around hills, mountains, or even the whole planet. So as sound is traveling this way, if it encounters, let's say, a wall or something, the sound is going to keep going that way, but it's going to kind of bend this way, okay? And it's going to form this little pattern, okay? Light waves can diffract through tiny openings, tiny slits. So if you have light or sound that's going through here, let's pretend this is the sound, and it's trying to go in through this little area, the sound or the light is going to kind of make this pattern, okay? X-rays can do also the same thing, okay? So all light and sound, they will behave like this. If there's an object here in the way, if there's a little opening, it's going to kind of do this. Or if there's, let's say, a little thing here in the middle, the light and the sound waves are going to kind of create these little patterns. Like I said, you're going to have to copy these in your notes, okay? There's no way around this. You have to copy this. Electromagnetic waves have a huge range of wavelengths. If the wavelength is of a similar size to a gap in a harbor wall, then the wave will diffract as shown. So right now I will play a video to show you. This is really hard for you guys to visualize, but in the video it's going to show you with water, okay? Because that's the perfect way of showing how energy is moving. So remember, any type of light is an electromagnetic wave, microwaves, X-rays, any of the 7 electromagnetic waves, infrared, they will all travel like this, like a wave, okay? And what better way to show how energy travels than with water, as we make waves of water, okay? So as that energy is going through and there's a little opening, when it encounters a little opening, it's gonna make this diffraction pattern. Okay, so here's another example. Again, copy these little pictures that are here, okay? So if the wavelength does not match the size of the gap, then only a little diffraction will occur at the edge of the wave. So if the opening's a little bit larger, it's gonna somewhat retain its original thing, but it's gonna kind of make that pattern. Okay. So I think what I'm going to do at this point is I'm going to show you the video.
What about light? Does light spread out after passing through an aperture?
Let me show you
Well,
the video.
here's an aperture